Yes, sir.
Yeah, so probably you are the only one here today. So do you have any doubt regarding the lectures and anything, maybe dislocations? Do you have anything to ask?
Yes, sir. I have to first the list connection
Hear
कितने
you
लेकर के
properly. Yeah, come again. Suraj?
सर मैंने लिखा है कि मुझे क्या क्या पूछना है उसमें से एक बार देख करके बता रहे हैं।
सुनाई नहीं दे रहा है सही से, एक बार फिर से बताओगे?
तो मैं बोल रहा कि मैंने लिस्ट बनाया है कि मुझे क्या क्या पूछना है तो मुझे एक बार उसमें से देखना होगा फिर मैं आपको बताता हूँ।
ओके, तो आज का क्लास शुरू करते हैं फिर, ठीक है?
यस सर ठीक।
ओके। Yeah, so from we have covered up to the rheology till now. Yeah, so we have covered up to rheology till now. So today we are going to start with deformation mechanism, right? So can you all see the screen? You can see the screen, right?
Yes, yes, sir.
यस सर।
Yeah, okay, all right. So deformation mechanism, we are in deformation, we are going to talk about the mechanisms that play at micron scale, or maybe in the microscopic scale. So for example, if we are seeing a fold or a fault, maybe these things, like what kind of deformation is going around. So this fault may be part of a rock, right? So the rock is basically made up of minerals, right? So there are minerals, like this is one mineral, this is one mineral. This is how rock is made up of. And this, now the mineral, if we zoom in into one particular mineral, they have particular lattice orientation, right? If I want to draw the lattice of a mineral, it will be something like that, right? So yeah, something like that. So depending on different crystal symmetry, maybe a mineral can belong to any of the classes that we know, right? There are 32 point groups and maybe around 230 space groups. So amongst those, a mineral can be from any of those groups. So depending on those groups, you have different kinds of symmetry. Maybe you have a hexagonal crystal, maybe you have cubic crystal, maybe you have triclinic or monoclinic crystals. Yeah, so there's that. But when you apply pressure, so if you are, so this is a rock, you are applying the pressure or force, maybe so from this direction and from this direction. So this force is also being applied at the mineral at the micron scale. So yeah, so this is some micron, maybe this some micron. Yeah, so it is, or maybe this is some angstrom, maybe it's not micron, it's much finer. So it's in the, so this is one particular element that is sitting at the particular lattice point. So we know about the lattice, right? Do we have any idea about the lattice? What is the lattice and why, what is the internal structure of minerals? We know these things, right? So that I can move on to the next part.
यस सर।
Yeah, so anybody want
यस
me
सर
to
यस सर।
explain, like why, how, what is the structure of a mineral and why I am drawing these dots? Anybody wants me to explain that? No one, right? Yeah. Okay. So moving on. So when we apply stress, so this stress is received by the crystal and it behaves in certain ways, right? So even if you don't have any stress, pure lattice structure, to get a pure lattice structure is impossible, right? So if you get the purest forms of crystals, even had impurities at ppb scale, parts per billion, right? So a crystal cannot be perfect, and it has these impurities. So what are these impurities? These impurities involve maybe this lattice, say for this mineral is formed of, say for example, A2B. This is the formula of this mineral. So what has happened, so for each B you have 2A, right? So this is the structure, right? So like here will be A, and again here will be B. So yeah, somewhat like this. So for example, SiO2, right? So this will be SiO2. So like silicon tetrahedra, you have a tectosilicus like that. So um you will have A, and then you will have B, and then you will have A, then again A, B, like that. So if what is meant by impurity is that, suppose in that regular arrangement of or the regular array, at some places you do not have neither A neither B, so you do not have anything, so that place is left blank, there is nothing. Those are called vacancies, right? And there is another kind of impurity where you get uh, different foreign materials, so foreign atom, right? No, not A, not B. This is if A to B, but that would not, that will not be included in the mineral formula. So there will be some other material like other atom, so it will be C, right? So and this C will be so the amount of C will be so less, and this will be so trace that we won't be including those things into the main formula, right? So we call them impurities. And what are the other kind of impurities that we may have? Like one positional mismatch, like here B is supposed to be here, but due to some reason the B is not here. Maybe one B is located here, right? Or maybe the B is little bit shifted or somewhere here. So in the interstitial may also get this atom. So these kinds of impurities are there, right? So and then you are so this is the condition of a natural crystal, and then you are applying stress. So what will happen? Let me open one of the PPTs. Yeah. So yeah, what will happen? This will, so this block, suppose this is one mineral, this is one crystal. So when you're applying stress from here, so what will happen? This will try to move, right? Are you getting this? This block, why they have constructed a block? Are you getting this? Hello?
Yes, sir.
Yeah. So now we're applying stress here. So what will happen? So there are lots of motifs. We call them motif. These points, we call them motifs, right? So there are they will try to move, right? But they cannot move. Like there will be some point or line, so they will be arrested. So the movement, for example, assume that this is the line after which there will be no movement initially, right? So this is the line where you won't get any movement after that. So what will happen? This part of the block, it will be squeezed, right? It will be squeezed little bit, and the overall this part will be little bit shorter, right? This will be little bit shorter. So this is the line up to which you are getting this movement in this plane. So this part will be little bit squeezed, right? So all this material inside, all these motifs inside this block will be little bit squeezed, and So but this does not happen instantaneously. It's not like you just squishing a block, or maybe giving applying some stress into a block, and in the microstructural level it just slips. It doesn't happen instantaneously. So there are some steps, right? It happens like if you just push this part, the upper part, so there will be, yeah, so there will be one kind of so for example, one kind of movement along these arrays, right? And after some point, when the first row, first column will shift, and there will be some columns which are no longer connected, right? So there you create one vacancy, right? So this won't be called vacancy at that point. That will be called dislocation. Why? Because you just move this part. So initially this green column is supposed to be here, but so this part moved, so now it is here, right? So and this will move, like when we apply gradually some more stress, this will again move to the right hand side, and the slip will be complete. So this is how this is a very simplest example of how a dislocation can move. A dislocation does move inside a sample, right? So it's like there are some experiments that is performed by Bragg. So basically these things were the crystallography, some very unique things that we study today, that are mainly most of them are you know, discovered by this person. So they performed experiments on bubbles to recreate the you know, what is happening when, you know, so these are the grains, right, inside the mineral. These are the grains, and this, yeah, so see, this is the grains that we see in the microstructures. So what happened when we apply stress? These vacancies, these little vacancies here, sorry, yeah, so these vacancies here, they move, right, when we apply some stress, so they move. So yeah, this is a very beautiful video. You can go through in the YouTube if you want to, you know, so learn like what is happening there and why it is analogous to the experiments, analogous to the mechanisms that happen in the nature, right?
Sir, what
So
is the title of this video?
uh, this is called, you search with bubble raft experiment. You can search in the bubble raft experiment. Otherwise, I will usually I share this PDF after the class. So I will share
Okay.
this today's whatever I am writing now. I will share that. So in the OneDrive folder, you will be having this link, right? So yeah, so this is how you see the dislocations move, and this is how when you deform the rock, or maybe in the nature when it deforms. So this kind of phenomena happen, but these are, as Bragg said, like these are very ideal condition. But for a visualization, for an initial visualization, you can see how the dislocations actually move, right? Yeah, so yeah, moving on. So yeah, so crystal, so most general term of impurity is crystal defect, right? So crystal defect is basically what I have just discussed previously. Like you can have vacancies, you can have interstitials, and like those things. So if in a mineral, suppose if in a crystal, if you are having dislocation at a particular point, so that is zero dimensional dislocation, so those will be called as point defects. So only maybe one vacancy is there, so some impurity is maybe there, some interstitial, like as it is shown here. Yeah, maybe there might be some kind of in some replacement of, say, any foreign material that is there in the lattice point. Maybe in the interstitial you can have that, so that will be interstitial impurity. This will be called substitutional impurity. And maybe you can have vacancies. So these are different kinds of point defects. All right. So for example, if you have ionic bonds crystals, say for example NaCl crystal, so there are two kinds of defects in ionic bonded crystals. So one is Frenkel defect, where you just like one lattice point is just replaced, I mean misplaced, so it will be sitting somewhere here. And in case of Schottky defect, you have one pair of anion and cation missing. Sorry, this will be cation, this will be anion. Yeah, so one pair of those will be missing. So these things are explained detail in the video. I don't think you will have any doubt regarding understanding those things. What I will describe now is what is Burgess vector, and what is line defect, and what is different kind of dislocation, say for example screw dislocation, edge dislocation, those things, right? So if you have an array of say there is some kind of distance between them, yeah, so there's some distance d, it's like that, so this d will be fixed, right? So for any mineral this is called d spacing. For any mineral, this d spacing is specific for that particular mineral, right? So is Burgess vector. So Burgess vector is basically minerals property, you can say, but it can vary 10%, but more or less this B, or you can call it Burgers vector. Yeah, so whatever you call it, it will be written as this. Yeah, so Burgers vector is basically the basis. So we know unit vector, right? We have a more or less clear understanding about what is a unit vector in a vector space. So Burgers vector is basically the basis of the displacement. Suppose you have a dislocation of 30 units, right? So those units is basically 30 Burgers vector, right? So it cannot have, suppose you moved one array, so one motif, it was initially here and you moved it somewhere here, so you cannot like move it randomly, right? So you have to, you will move it by the multiples of some Burgers vector. So this is how dislocation happen, like one array, then the other, then the other, so they slip like one by because the mineral has to the preserve its despacing, otherwise it will be an entirely different mineral, right? So by deforming a mineral we don't change the structure actually. So what happens is that you shift those arrays, and those shift, there is a minimum value of that shift, and that is Burgers vector, right? So
Sir,
yeah,
sir, the unit Burgess vector always defined on the scale of atomic. I mean, on the atomic scale.
not at what do you mean by atomic scale? It's not subatomic scale. So it is the spacing between the two. What is like, say for example you have a, okay, I'll just, yeah, so suppose you are deforming this, okay? So this array or this column will move up to here or here or here, right? So maybe if it moves here, so there will be three, but it will move three Burgers vector, right? Three times b. If it moves here, it will be one time one, it only b. If it's here, then it will be 2b. It cannot move anywhere, right? This fellow, he cannot move anywhere in the crystal, like he cannot move anywhere here or maybe here, no. So it has to, so ultimately when you get the final picture, it will be sitting either here or here or here, that if you continue the deformation, this whole part will again move in this direction, right? And this fellow will be sitting, now it is sitting here. If you continue deformation, after some point it will be it will be sitting here, after some point it will be sitting here, like that. Are you getting my point?
ये सर मेरा ये डाउट था कि जो हम ये डिस्कस कर रहे हैं वो हम लोग लैटिस स्केल पे ही तो
Ha 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 ha
मतलब
ha.
ये सारे
Everything we are
कर रहे
it's
हैं
like
तो
this is one silicon, this is one oxygen, like that.
यस सर
Yeah. So suppose you are getting movement along a particular, suppose, so the yeah, just okay, yeah. So when you are moving this upper block, maybe in this direction or this direction, so just so there will be one line that will be produced, right? So that will be the line at which the slip is happening. So after that there is no slip, but before that there will be slip. All right. So this is called actually the line defect. And so line defect can be screw, so dislocation, I mean line defect can be screw dislocation or edge dislocation. So what is happening, if you just move this upper part into the right hand side, what will happen? So Burgess vector, it will be directed rightwards, right? Because we are pushing this whole block in the right hand side, right? So the Burgess vector will be, so we are pushing this whole block into the right hand side. All right. Why am I not being able to? Okay,
सर
maybe.
ये डायग्राम सर मैं भी समझ आया मुझे ठीक से, ये
Okay,
सर इस
yeah. uh okay, no. Okay, so this upper part, so up to here the sleep has happened. So after that there is no sleep, so the configuration was like before, right? But from here some kind of sleep happened, right, along this plane. All right. So there will be one line passing through the, inside the crystal. So this, along this plane, this upper part slipped, this upper block slipped. All right. So this upper block moved in this direction, so the direction of the Burgess vector will be this one. So what happened, you just slipped the upper part, right? So the direction of the Burgess vector will be along the slip direction. Clear? Are we clear?
सर ये समझ आ गया था उसमें सर एक अलग तरीके का मतलब वहाँ पे भी स्लैंट सा दिखाया गया है.
Okay, so there is another parameter that is called the tangent to the slip line, so that will be t. So in case of edge dislocation, this b will be perpendicular to t. All right. So there is so ये समझ में आ गया ना इतना तक? हाँ. So and the another part is, it's like screw dislocation. So what happens, so instead of just pushing the whole block, it's like tearing a paper. So imagine what you do if you tear a paper, what you do, it's like some part of the crystal. Okay. So now imagine the same thing is happening here. So what, instead of this whole line, whole plane is going from here, so overall this line is actually going in this direction. So you are just tearing the upper part. All right. So defect is moving along this direction, but the movement, so what will be t, the direction of t? So this t, it is uh, so now are you getting this? Because here the like this line was initially here, all right? So now you just it's like tearing a paper. So when you are tearing this paper, so this front will go in this direction, in this direction, right? But this is the dislocation line.
सर जैसे अगर मैं कह रहा हूँ कि जैसे टीयरिंग पेपर को टीयर कर रहे हैं तो जो इसमें बर्गस वेक्टर है और ये टी वेक्टर है दोनों ही सेम डायरेक्शन में है इनसाइड द पेपर, तो ये सही है
Inside the
परपेंडिकुलर
no so that paper will be this plane, right? This plane. Paper
यस
is not this plane. Okay, so this paper will be this plane, the left hand side plane. So the Burgess vector will not be inside the paper, right?
इनसाइड मींस सर पेपर के अलोंग नहीं पेपर के
Ha,
परपेंडिकुलर
perpendicular,
इनटू द
yes.
पेपर
Paper the Burgess vector will be the perpendicular to the paper.
बट
So
वो
will be T.
यस सर
Hmm?
यस
Is this clear now?
एक जगह था जहाँ पे सर ने जो निकाला डायरेक्शन वो कुछ अलग तरीके से कर दिया था वो
Ha,
यही
wo,
इसलिए confusion हो
yeah,
गया
so that was different, maybe. Um, are you talking about? No, so it is not here probably. So it is in the video, I think. Right? So you only considered this image. Okay. So this image, this is right. All right. So he actually may have drawn here, right? So the
ये इसके बाद सर था उसमें 4 डायग्राम थे सर साथ इसके नीचे शायद
here.
हाँ यही वाला ये सर
So this is not the Burgess vector. Okay.
हाँ
So
यही सर
this is not, this is the direction at which the slip front is moving. So here this slip line is moving in this direction, and here
यस
the slip line is moving in this direction, but the movement of the block is always in this direction. Here also it is in this direction, in this part also it is in this direction. This is the direction of the, so you can say this is the direction of the Burgess vector.
जो हम कहेंगे डायरेक्शन ऑफ डिसलोकेशन तो सर डायरेक्शन डिसलोकेशन बर्जेस वेक्टर ही है या फिर ये जो दिखाया गया ब्लू एरो उसको डायरेक्शन ऑफ डिसलोकेशन बोला जाता
Ha. So this is basically the movement of the slip lines.
है सर
So in
वही मैं पूछ रहा हूँ कि मूवमेंट ऑफ स्लिप लाइन ही को डिसलोकेशन डायरेक्शन में बोलते हैं या वो अलग है
no, see the direction at which these atoms are moving, like here the atoms are moving what in the right hand side direction, right?
यस सर
And here also if you consider this part, the atoms are moving in the right hand side direction,
यस सर
right? So it is not moving, the atoms are not moving in this direction, it is moving in this way, in this direction.
यस सर
So this will be the direction of Burgess vector, Burgers vector, whatever.
एंड डायरेक्शन डिसलोकेशन
Direction of dislocation meaning?
डायरेक्शन ऑफ डिसलोकेशन कुछ नहीं होता है
So dislocation line is moving here in this direction. So this blue line is marked.
line yes sir,
Yeah,
direction dislocation
yeah. So this dislocation line is moving in this direction for edge dislocation, but for screw dislocation, it is moving away.
डिसलोकेशन लाइन इसमें डिसलोकेशन लाइन का जो डायरेक्शन है
हाँ.
वो राइट टू लेफ्ट होगा या फिर इनसाइड आउट होगा नीचे वाले डायग्राम में
नीचे वाले डायग्राम में it will be inside out, मतलब inside from the outside. The direction of the movement of dislocation line, right? So it will be inside. So this blue arrow, if you follow this blue arrow, this is how this particular line will move.
हम सर कह सकते हैं कि जो डिसलोकेशन लाइन है वो इस डायरेक्शन में मूव कर रहा है जो यहाँ पे शो किया गया है
हाँ.
बट जो डिसलोकेशन लाइन है उस लाइन का जो ओरिएंटेशन है या डायरेक्शन है वो किधर है, वो उसको हम लोग बोल सकते हैं कि राइट और लेफ्ट में है।
ये जो लाइन है, if we move this, if we move whatever you have in this crystal, if in this block or this part of the crystal, so if you move this part, this upper part, it's like if you have something, if you move that upper part, so this line, so this plane will be extended, right? So this line will be shifted to in this direction, so this part will be shorter and shorter, right? But here this plane will be extended along this arrow. So this yellow plane will be extended along this arrow, and ultimately you will get this. So you will, you know, you will form the same thing, but here it just moved in this direction, and here, so dislocation line moved in this direction. So in one way the dislocation line moved in this direction, and in this case dislocation line moved in this direction.
Yes sir, sound clear.
Okay.
Yes sir.
Yeah. So uh, if you have any doubt you can ask, so that is not a problem. If you are still have any doubt you can always ask, right? Okay.
Yes sir, thank you.
Okay. Yeah. So yeah, where were we? uh Sorry. Yeah. So now when a dislocation moves, it cannot like simply we call when something, so there is a plane, right? There is a plane of dislocation where along the plane it is moving, so that kind of movement is called glide. But if you have some kind of atoms in between the path, or maybe some kind of vacancy, so that plane, so it will have to create new planes on the upper level, right? So if it's moving in this direction and now it's experiencing something, some kind of obstacle in its path, so it will stop growing in this direction, and it will climb, and then again it will grow where it doesn't have any more, you know, obstacle. So these are called climb. So but climb you need higher energy. So it has been seen in the optical, not optical, in the experimental procedures, that when you run the calculations of, so you need more energy to do that. So we say that climb we need a much higher temperature. For glide we need a lesser temperature than we need for climb. All right. So yeah, so these are more or less self-explanatory. So one thing I want to just say that we all have seen quartz grains, the undulous dislocation of quartz grains, right? So if we have a quartz grain, and inside that quartz grain if we see the undulous dislocation, so undulous extinction, so those little domain, right? If this is a quartz grain, and inside the quartz grain we are seeing some patches, right? So this is one single quartz grain, right? So we are seeing some kind of patches inside that. So the extinction angle of this part is it's slightly differing from the extinction angle of this part, right? There is the difference, but the difference is very subtle, difference is very less. So this boundary, it happens because of the orientation of the lattice at this point. If I draw the lattice, maybe the lattice is oriented here, is slightly different than the lattice which in this domain, right? It's slightly different. So these boundaries we call low angle grain boundaries. But if you have another grain beside this, another quartz grain beside this, so the if the orientation is somewhat here, the orientation will be in very different here. So the difference of orientation, or maybe you can say the misorientation of this grain and this grain, will be much larger than the LAGB. So we call them high angle grain boundaries. These terms are important. Like if you pursue like deformation mechanism in higher studies, you will come across these terms. Otherwise, it's not really that important. Yeah. So, but for example, there are other kind of surface defects or boundaries. Say for like here it is some twin boundaries, as you see in case of, suppose you are seeing a plagioclase grain in under the microscope, and you will see if this is the plagioclase grain, you will see like one clean division, like maybe this part has already extinct but this part didn't. That also happens because of the mismatch of orientation, right? And those form due to this kind of deformation, right? Yeah. So I'll move on to the next part, which will be discussing what is the macroscopic behavior. So we just discussed like how these things operate at a very very fine scale, very little, very small scale. So rock, when it deforms, it doesn't necessarily always form this kind of ductile behavior or plastic behavior, right? Sometimes what happens is that you have a aggregate of grains and we apply stress, and we just like these dislocations, to move these dislocations we need some kind of vibration, some kind of energy, right? The temperature has to be higher than a threshold after which these kind of mechanisms get activated. But before that, what will happen? Some kind of fracture will develop, right? So a grain will be crushed and it will form new grains. So here what is happening here, the grains are crushed in this region, and so some daughter grains will form from the mother grains, and you will end up by reducing the grain size. So this is also one kind of deformation where you reduce the grain size, but this is a brittle kind of deformation. And the macroscopic effect of this is
सर
granular yeah.
इससे पहले स्लाइड पर सर, हाँ ये
Hmm.
इसके नीचे वाले,
Hmm.
हाँ सर, इसमें सर मैंने ईमेल से भी पूछा था सर, तो
Hmm.
आपने बताया कि इसमें जो है डाइजेशन की वजह से जो है इसमें
Hmm.
आ जाता है सर।
Hmm.
इससे जो ये तो ठीक है, ये जो हो जाते हैं डेंसिटी कम हो जाती है, लेकिन सर इसका साइज कैसे बढ़ जाता है?
What size?
जो ग्रेन्स हैं उनके ग्रेन्स के बीच ग्रेन्स का जो है साइज वो कैसे इंक्रीज होता है?
Okay, so mm, suppose you have a grain here and you have a grain here and one grain here, right? So in between that you have this in between that you have a pore space, all right? Now dilation is happening. Okay, so if dilation happen, what is actually happening? So this grain, so not really like not like, so yeah, that will not be a good picture. So what when dilation happens, so this grain will move somewhere here, and this will move somewhere here, and this will move somewhere here. So this space is now this much, all right? So the pore space is increased, right? So if you have, like, if you are you are dilating the entire thing, right? So when you're entirely so, but in the grains cannot grow because we do not have given them any reason to grow, right? You are just increasing the space that is occupied within this grain, occupied by those grains. So what will happen, the interstitial space where there were, like, it was small previously, what will happen, those spaces will also so spaces will actually increase, all right?
यस सर।
Okay. Okay. Yeah. So yeah, this is the natural example of, I mean, the macro scale example of what happens when you have a cataclysmic flow. So it will happen, so cataclysmic event. So what will happen in the, so its response in the macro scale will be granular flow, while you will be having landslides, all right? So in the micro scale also you can see, like here you see how the grains have crashed. So one big hint to identify a cataclysmic event is that the grains that will form out of those events will have very sharp boundaries. So if you form a grain or maybe two or
सर
three grain, yeah.
इसमें सर एक जगह लाइन ये लिखी है कि ब्रिटल फ्रैक्चरिंग जो होती है ग्रेन्स की,
Mm-hmm.
उसमें जो एनर्जी रिक्वायर्ड होती है वो एनर्जी लेस होती है उसको रोल करने के कंपैरिजन में। तो सर ये नहीं सुना है कि किसी को रोल करने से में एनर्जी ज्यादा कैसे लगता है और उसको फ्रैक्चर करने में कम कैसे लग रही है मुझे।
Okay, so
कैटाक्लास
suppose you have say for example, you have a, what kind of say, some kind of object, some kind of heavy object, right? And you want to move it. Or suppose you have a sack of say uh, rice. Okay, so you have a sack of rice, right? And you want to move it. So it's like deformation, right? So imagine those sack of rice is basically a grain, one single grain. So if you roll it, you will need less energy, right? But if you want to tear the sack and move some part of the rice, so that will be needing much higher energy, right? Right.
यस सर।
So yeah, I think that answers your question.
सर बट
Yeah.
सेंटेंस उसका अपोजिट लिखा हुआ है
Sorry, kaha?
सर। कैटाक्लासिक में जस्ट लिखा हुआ है। कहाँ से कैटाक्लासिक, हाँ ये सर फर्स्ट सेंटेंस इसके पीछे जस्ट पहले वाला
This one?
ऊपर। नो सर ऊपर दो सेंटेंस सर पॉइंट फाइव में लिखे हुए हैं। एक यही सर इसमें ऊपर से देखिए जो लिखा था।
Okay. This thing I'll have to check, and I will reply in one email maybe. Okay. Because I don't think, if you have, say for example, so it depends. So this sentence is not, I mean, for a, see, this depends. So what my example is a little bit flawed here, because if you have I mean the cohesion inside the matrix or if the cement is very high, then to roll that will be difficult. So what will happen? So it won't roll, one fracture will be created. All right. So what happens first? So we are talking about granular flow. All right. So in granular flow, the materials are very loosely consolidated. Right. So for a loosely consolidated material, it is easier to roll than to fracture. But if you have a consolidated rock, then the cohesion will be very high. So in that case, before rolling, fracture will happen. So the idea is whichever is happening first requires less energy. Are you getting my point?
यस सर यस सर।
Yeah. So as I was talking about the granular flow, so I thought that okay, you're talking about loose sediments. All right. But if you have a rock which is very compacted and have a very consolidated, what will happen? So the fracture will happen first. All right.
यस सर।
Yeah. Yeah. So does anyone else have any question? Has any question? You can also ask. All right. Okay. So the grains will be angular, and we call them brachia. So there is that. And that is more Coulomb failure criteria. So we don't have. Do we have any problem regarding this, Tushar? Regarding more Coulomb criteria? Okay. Okay. So if they have any problem, then I will explain what is more Coulomb criteria. But I think we are little out of time here today. So I'll quickly go through the third lecture also. So yeah. So as I was talking about Burgess vector, this is the this one equation that is called, this will be strain rate, so epsilon dot. Okay, so this is the Orovan's equation, which describes mathematically how Burgess vector and dislocation density, which is rho, and the speed of the movement of dislocation is related, right? So if you strain a material, if you apply some stress, if you strain a material, so that will have strain rate can be expressed by these three terms, right? Okay. So yeah, I was talking about like why we need to cross some barrier for climb to happen. So if you observe the micro, say for example, you are observing one microstructure at 400 degrees centigrade, and you are observing one microstructure at 600 degrees centigrade of, say for example, quartz. If you have a quartzite, you are deforming the sample, or it is already deformed in the terrain, in the natural processes, and you are observing those two samples. So it will be like people have performed experiments in the laboratory scale, and they have said like there is a threshold in between 400 and 600, maybe 200 or 300 and 600. So in 600 the climbs will happen, because when we increase the temperature, what is happening, so the grains, so what is the temperature is the emancipation of the movement along its mean position, right? So the motif is basically vibrating at a higher temperature, and it will be easier for them, to climb or to surprise any kind of obstacles that it happens to be on their path, right? So yeah, there's that, and this is the equation that tells like how dislocation glide happens. And yeah, so if you have an aggregate of rock, suppose you have a mineral like this, so what is happening, like if you deform this rock or deform this single grain, so as a result it's experiencing, so there is a bulk stress, and so suppose this grain is experiencing the stress in these two direction, so what will happen, so there are lattice right inside, so the lattice, the motifs will be arranged in some regular way before experiencing any kind of dislocation, any kind of dislocation movement, any kind of deformation, right? So when we apply this stress, what will happen, this dislocation will move, right? So it will move, and after some point it will produce some kind of dislocation line, right? Suppose the line is like that. So if you continue doing this process, application of stress, what will happen, so dislocation line will be entangled, right? So it will always be on the boundary, because on the boundary, so always it gets free surface, right? So but inside this, it will travel along the boundary initially. uh, so what will happen, so there will be some dislocation tangle, we call it dislocation tangle, right? So so in the nature always there is a process, like it wants to come down to a lower energy state. So to do that, what it will do, it will just increase, or the boundary will be expelled outwards, right? And it will form a new region where the lattice will be again rearranged. So this dislocation, this will move outside, and that part of the grain will be free of dislocation, right? The material is same, but you will end up by forming a grain which is like that, right? So this process is called bulging, right? And if you if you produce enough bulge around the grains, and if you produce like small grains after that, after this, so this will be closed, and this part will be separated out from the mother grain. So if you end up producing these daughter grains from the relict mother grain, we call them bulging recrystallization. Okay. So and if you increase the temperature of deformation, or if you increase the deformation after, like say for example, this happens at a temperature around 300 degrees centigrade, say for example, So and after that, if you are around 400, so this is actually mineral specific, all right. So if this happens for, it doesn't mean that for quartz, if it's happening at 300 degrees centigrade, for feldspar also it has to happen at 300 degrees centigrade. So the bulging may, for feldspar, the bulging may initiate at 400 or 500 degrees centigrade, right? So it is a mineral specific range. Okay. So after that, what happens, what we see that the entire grain, so when it's done, forming bulge and forming this kind of dislocation, the entire grain there, it produces some kind of low angle grain boundaries, right? And so subgrain form. So this is an entire grain, so the part of the grain is oriented in a way that you are having, like, if this is one array inside the grain, so it is now like is oriented like this, and the entire grain will now then be separated. So the entire mismatch, it increases in a mismatch, or misorientation will increase, and you will form a new grain. So those are called subgrain rotation recrystallization. So these processes are called subgrain rotation. If you increase the temperature more, then what will happen? So these grain boundaries are no longer. So initially, what we are seeing, like initially, the grain boundaries are forming little bulges, and then new grains are forming out of them. And then we saw, like, the part of the grain is changed its orientation, and subgrains are forming. But now at higher temperatures, say for example at 550 degrees centigrade, what will happen? We will see grain boundary migration. So the entire grain boundary will move to form new grains. So like this part will actually formed another grain. So it will be something like that. So one grain will be in the microstructure, you will see this kind of grains, right? So it will be possible for the grain boundaries to readjust and create new grains which are strain free, right?
सर
Yeah.
इसमें सर मुझे थोड़ा सा जैसे डाउट है
Hmm.
सर, जो जैसे बीच वाला ग्रेन आपने सर ड्रॉ किया है उसमें जिस तरह का शेप है
Hmm. Yeah.
कोई फिगर
Go on.
सर डायग्राम से ही पूछना है वो सर जो आपने डायग्राम बनाया था वही वाला मुझे।
अच्छा.
हाँ सर, जैसे अगर हम इस तरीके से देखें तो अंदर वाले को समझें तो हमको लगेगा कि ये बल्जिंग आउट हो रहा है अंदर वाला, और अगर बाहर को देखें दूसरा उसके अल्टरनेट जो हम देखेंगे तो हमको लगेगा बाहर वाला अंदर की तरफ बल्ज हो रहा है।
Yeah, okay, yeah, all right. So the
तो पता
thing is, so the new, so if you look under the microstructure, or if you do some analysis, say for example EBSD or something like that, so what you will see, so under the microscope you won't see any kind of strain. Or so what happens, how to identify the strain, that the grain will be the extinction won't happen at the same time throughout the grain, right? So there will be undulous pattern. So inside that, as this is a relict grain, inside that you will see those domains of extinction, but outside these new grains will be extinct at the same time. So you can say that from that observation, so these grains are strain free, right? So the grains which are strain free will be the daughter grains, not the mother grains can't be strain free, right? Suppose you have a grain, you are deforming it, so it will produce undulous extinction inside that. You know what is undulous extinction, right?
yes it forms due to deformation,
Yeah. So now,
maybe like extinction,
sorry.
wave like extinction they
Yeah.
can do.
So now if you are producing new grains along the boundaries, suppose these grains are produced, right, along the boundaries, and now here is your mother grain. So these grains are produced from this grain, right? So here you will see the absence of undulous extinction. But here the mother grain will show undulous. So then you can say like which are the daughter grains, and of course there will be a size difference, huge size difference. So for example, if you are seeing, see, this is the parent grain, right? And these are the daughter grains. So can, and you see like here, so it is being showed that the grain is showing undulous extinction,
Yes,
but
sir.
these grains are free of that, and the size is also very small. All right. Hello.
Yes. Yes, sir.
Okay. Okay. Yeah. So yeah, so this is the curve at which, so first you initiation of dislocations, and then bulging, and then subgrain rotation, and then grain boundary migration. So these are usually, so this is a hypothetical curve, but you can see like at what point these things happen, right? So this is a good representation of the microstructure of rock. So but the dislocation, what is the process or the physical process at which, in which the dislocations actually move, right? So just one sec. Yeah. So um, these are divided into three parts. So one is dissolution, precipitation, creep. So one, that is very simple. So if you apply pressure, so when we apply pressure, the concentration of that particular phase at that particular space is basically increased, because in the pressure term is there inside the equation. So the equation was written somewhere here. Yes. So the pressure term is there. So due to this pressure term, the equilibrium concentration, so the concentration is more than the equilibrium concentration, and it get dissolved, right? So when it get dissolved, so I think that will be less. Yeah, that will be less, and it get dissolved. So, and when that is a tensile state, the concentration will be more than the equilibrium concentration. So it travels to the tensile part, and it get precipitated there. So this is how dissolution precipitation creep works. And the another part is the diffusion creep, where the vacancies move maybe through the grain, or maybe along the boundary of the grain. So if it moves through the grain, we call them Nabarro herring creep. If it moves along the grain, we call them cobble creep. All right. So yeah. So in never wearing creep, these vacancies move through the grain. As you maybe recall when seeing the video, like within the grain, a vacancy is traveling, right? So if it moves through the grain, then we call this never herring creep, and it is moving along the boundary, then we call it cobble creep. So the equation is a little bit different into these two. For example, as cobble creep is responsible for grain boundary surface diffusion, the vacancy diffusion along the grain boundary surface. So it is more dependent on the grain size. So if you have a very small grains, then the diffusion will be much faster, because it has to travel a much shorter path, right? But yeah, but they are more or less like inversely proportional to the grain size, which is very important point, because when you're studying the diffusion creep, you will see that diffusion creep is basically is hugely, it's mostly dependent on the grain size. So if you have a grain size which is much less, then the diffusion creep will be very much faster, right? So yeah, I think that will be all for today. If you have any more questions, then you can ask. Otherwise, I will stop the
Sir,
session.
I have one question.
Yeah.
I asked why presence of partial fluid reduces the effective confining pressure.
Why the presence of partial melt increases the
Partial,
effective pressure?
uh,
Yeah. So it's like that. Suppose you have, say for example, so it depends, right? So mostly, if you have a material which increases in volume, when it changes its state. Suppose its material is solid and now the material is liquid. So if the volume expansion happens, what will happen? It will exert some force. All right.
Yes, sir.
So that's how effective pressure is increased. So the the pore pressure is increased.
नेट फोर्स जीरो हो, मतलब रिड्यूस हो, वो सब समझ में आ रहा है, लेकिन प्रेशर कैसे? जैसे अगर कोई मेरे पास कोई ऑब्जेक्ट है, उसको एक साइड से प्रेस कर रहा है और फिर दूसरे साइड से भी प्रेस कर रहे हैं, तो सर प्रेशर तो बढ़ेगा ना, घटेगा कैसे?
Okay.
जैसे बलून जो है,
Where it is written? In cataclasis. It is not written here. Suraj?
in cataclysmic deformation.
So in lecture 4, deformation mechanism 4.
Yes, sir. 14 लिखा हुआ है सर, I guess.
Where
ग्रैनुलर के जस्ट नीचे.
granular ke just niche. Oh, not this one. Not this one either. This one, right? Granular flow ke niche.
हाँ सर, थर्ड इसी में ग्रैनुलर फ्लो में ग्रैनुलर, इसमें ग्रैनुलर के बारे में लिखा हुआ है, इसी में थर्ड नंबर.
Where it is written that the effective pressure will decrease or increase, whatever you are saying. This one.
सर थर्ड नंबर. यस सर.
Okay, so it is like high effective pore fluid pressure. So it's pore pressure, right? That is what I am saying. I was saying. So inside the material, so this is the pore space. This is the pore space, right? So you are melting this part and the material is accumulating here, right? So the material is accumulating here. But by the property of this material, if it undergoes transform from solid to liquid, it will increase its volume by the property. So there is a fixed pace. Suppose this is the pore and you had some kind of material there, and when you are adding more and more material, so what will happen? How much you are going to, like, suppose you are melting this part, so by volume it will, it wants to acquire more space because it, the volume increases after melting. So it will increase the pressure along it will exert the pressure along the wall, na? So like this was the previous instance, right? So now you are melting, so the boundary is getting melted and now you have this much area, but by the property you need larger area than to accommodate all the melt. You need maybe this much area, right? Larger area than this one. So what will happen? But the material cannot go there because this part is already solid, right? This part is already solid. So what will happen? It will exert pressure along these walls, na? So this is how the pore pressure will be increased. Are you getting the point?
Yes, sir.
Okay. So this is what it is written here. So great depth, because at great depth you cannot usually accommodate this liquid. So in liquid, if it increases its volume, then this won't, suppose for if you want to just imagine, like you have ice at that great depth, right? So but ice, what happens, like when it melts, it reduces volume. So it doesn't happen with ice. But it's not possible to have ice at the normal ice state at that particular temperature and depth. But if ice like material was there, then that won't be happening for ice. But material which expands in volume when melted, so they will increase the pressure, effective pore pressure. All right.
सर तो एक्सपेंड करने के लिए स्पेस भी तो सर वहाँ पे होगा तब ना एक्सपेंड करेगा, जैसे अगर मेरे
नहीं,
पास कोई
no, expect. See, if you are increasing the temperature. Suppose we are melting this thing. Okay. So, and it is occupying some space in the air, right? So you are melting this thing. So what will happen? It will melt at first. So melt doesn't. I mean, melting process is not related to whatever space it requires, right? So melting will happen if it passes some kind of thermal threshold, right? So it will lose its bonding as a solid material and it will melt. So now it has to accommodate space. It has to accommodate itself in a space. So it will be wanting to accommodate itself in that the provided space, but the provided space will be lesser than whatever is required for it, because the volume got increased due to melting, right?
सेकंड नंबर पे ये लिखा हुआ है कि लो कंफाइनिंग प्रेशर पे होता है, बट हाई पे भी हो सकता है अगर पोर प्रेशर हाई रहे तो ये मतलब सेकंड नंबर पे लो बोला गया है और थर्ड नंबर पे हाई।
कौन सा सेकंड थर्ड, कौन सा सेकंड पॉइंट?
इसी में सर सेकंड पार्ट पर ही द फॉर्मेशन ऑफ
See,
अनलिक्विफाइड
this
मीडिया।
is this is high pore fluid pressure. So this is the pore pressure. This is the confining pressure. So granular flow happens generally at low effective confining pressure. So like in the upper part of the crust where the material can easily lose its contact.
यस सर।
But when you go into inside the depth, the granular flow to happen is not easy. So there is high effective confining pressure, and to happen the granular flow you need to lose the cohesion first. So that is not possible, but that is only possible when you have a high pore pressure. So what will happen, the pore will exert
ओह
some. Huh?
यस समझ गया।
uh,
जब पार्शियल मेल्टिंग हो जाएगी तो उसका रोलिंग करना इजी हो जाएगा।
हाँ, उसको, या उसको लुब्रिकेशन भी मिलेगा. So those
हाँ
things are there.
हाँ यस सर हाँ सर। जो मटेरियल उस पे उसको रेजिस्ट करता मूवमेंट, वही मटेरियल उसके मूवमेंट को सपोर्ट करने लगता है
Yes,
जब
yes,
मेल्ट हो
yes,
जाता है।
yes, yes,
यस
yes,
सर।
you're right. Yes, yes. Okay, so I think that will. Do you have any more question? Hello.
नो सर, एक सर था आपको पिछले क्लास में से छूट गया था, लाइव सेशन में सर आप बता रहे थे तो मैं सर कुछ काम था तो चला गया था तो वही बचा है। अगर
हाँ,
आप लाइव सेशन देख लेंगे तो उसमें हो जाएगा, अदरवाइज वही नहीं
हाँ,
चलेगा।
हाँ. तो तुम एक काम करो, तुम वन ड्राइव में जो फोल्डर शेयर किया गया है ना, तो
हाँ
तुम उसमें जाके तुम्हारा जो भी, मतलब एक क्या 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 नाम है उसका, तू शो यू दिस. So yeah, problem solving session. So if you click this tab, you will be redirected to an OneDrive folder. All right. So here you will be able to see like what is the. Okay, so it is, the link is not here. Okay, I will upload the link. See, the video is already uploaded. I'll upload the link here and today's also. So from here you will be able to go through the that class. Okay.
यस सर।
Okay. Yes. So yeah, so that will be all for today, I think. So we'll be meeting in the next day. So yeah, in the next day we will be discussing about foliations and falls. Also up to this part we learned about the mechanisms and all those things. So after week 8, it will be about the manifestation of different kind of structures and from where and how we are going to explain them, right? So with all this knowledge we are going to learn this foliations, folds and falls and all those things. Okay,
सर,
so yeah.
जो सर हम लोग का फाइनल एग्जाम होगा उससे रिलेटेड सर कुछ सैंपल पेपर भी कहीं मिल सकता है, या फिर सर डायरेक्ट वहीं देना होगा मुझे?
uh, you are getting assignments, right? Weekly
यस।
assignments. Yeah, I
यस।
think the questions will be more or less like that. I mean, not so difficult but not so I mean, but it will be more or less like that.
ये ओके सर।
Hmm. Yeah, so that will be all for today. Thank you.